Hi everybody, in this video we are going to talk about the Gauss Markov Theorem. Let's go. And the assumption that's given the previously of the linear regression model, the estimator of the beta 0 OLS and beta 1 hat OLS have the smallest variance of the all linear and unbiased estimates of the beta 0 and beta 1. If we draw this is the population. If we draw the population and we will extract from here that's the sum sample, the population regression function is equal to the yi is equal to beta 0, beta 1 xi and plus error term I, and the sample analog of our population is equal to yi is equal to beta 0 hat plus beta 1 hat xi, the plus the error term hat I, the residuals I. And we making it the sum inference to look into our sample using the method of the ordinary least square, and we estimating our estimating population beta, the look into our sample beta. To do so, we're using the ordinary least square estimator, which we previously discussed in our videos. Here the best, the blue, they are the blue of beta 0 and beta 1. B refers to the best, which is the ordinary least square method. L refers to linear, the linear to be the parameter. We have the previously discussed the linear in two sense, linear to parameter and linear to variables. For us it's important to be the linear to parameter. Unbiasedness. Unbiasedness refers to expected value of the beta hat is equal to beta 1 itself, which we call in true beta. Estimator refers to the probability limit of beta 1 hat and increasing to infinity my beta 1 hat, they converge to my true beta 1. From the video that's the properties of the good estimator, we say that the estimator are unbiased, consistent and efficient. The probability limit of beta 1 hat equal to beta 1 refers to the consistency, and while that's the variance, suppose that we have a two sample, we estimated from the sample 1 is the beta 1 hat, and there is from the estimated beta tilde from the sample 2. If that's the beta 1 hat is the less than the variance of the beta 1 hat, the less than variance of the beta 1 tilde, in this case we consider beta 1 hat is efficient. Let me draw the graph to represent in graphically to make the more sense and visible. We start from the unbiasedness. Unbiasedness, as we say, this refers to the mean of my population and sample is equal. It refers to the mean of my estimated beta 1 hat is equal to my population beta. Both of them is equal. We estimated my probability distribution of my beta through ordinary least square estimation technique. Now this is the graphical representations of my unbiasedness. Whenever we say unbiasedness, this should come to the mind, this graph distributions. And we here the previous we derived that the beta 1 hat is equal to beta 1 plus that's the summation of the x minus xi. I write there they consist of the two parts, the non-stochastic part and it's the random part. We prove here that's the beta 1 hat equal to beta 1, which is the unbiasedness. Here the parameter best second L, the parameter from this population, we can see this is my parameter beta 1 and beta 0 and beta 1. Straightforward is the linear. Let me make the graph of the consistency. To make the graph, that's the y-axis is my frequency of my y and x this one. If we draw this one, it's the, let's suppose it's the, we have this the two sample. It's my first sample consists of this the 100 sample size. They consist of this the 100 observation, and this is my distributions, and this one also is unbiased. My beta 1 hat is equal to my beta. If we will increase in probability limit, means it's increasing our sample size to thousands. Let's suppose it's 1,000 observations, and they converge. They will converge to more to my beta actual, beta true. This one we can see in the graph. By increasing the sample size and my distribution, the graph, they converge the more to my true beta. And we call in this one is the consistency. Next, let me make the graph how they looks like efficiency. This is what my frequency, this is my x. If we making it the distribution of my two samples, sample 1 is beta 1 hat and the second one is it's beta 1 tilde. Still there is it's the efficiency. This is my two sample 1, sample 2 is efficiency. Because of it we write in this the expected value of the beta 1 hat is equal to expected value of the beta 1 tilde, and this one also is equal to my beta 1 through my beta, the population the beta. Which one we call, this one we call this the unbiased. The both sample is unbiased, but which one is the more efficient? Which sample estimate beta we will choose? From which sample estimated beta we should choose? First one, this one estimated from the beta tilde. The second one is the yellow color, the distributions. This one estimated by my second sample, which is the beta 1 hat OLS. And from there, which one is the efficiency? We can see from here the yellow color, they have this the less the variance, they have this the less variance, and we can conclude there beta 1 hat is more efficient than beta 1 tilde. This one also refers to efficiency. That's all for today. Thanks for watching my video.